All right, how's it going, everybody? We are here in week 5. We got lecture 2 of week 5 here today. Um, I thought I just changed this thing right here, did I not? Sorry. Let me fix my sign on the left right here. So yesterday we talked section 4.1 uh, and a little bit of 4.2. Today we're going to wrap up 4.2. And we're going to get into 4.3 here as well. These will be the only sections that we're actually going to cover out of this chapter right here. So we'll pick up with chapter 5 next week. Um, and so yesterday we looked at expected value of a random variable, a discrete random variable, and importantly. Um, Monday. All right. So we looked at expected value uh, last video here, but we did not look at our standard deviation of a discrete random variable. So we want to go ahead and look at that today. We'll also look at section 4.3 today, which will be about the binomial distribution. How can we expect results to be distributed if there are only two possible outcomes and a known probability of success? So we'll pop into Excel for a bunch of calculations at the end of today. So last video, we did look at expected value computations, but we did not look at standard deviation computations. Fortunately, the standard deviation computation is very similar to our previous standard deviation computations. It's really sort of like a combination of how we did standard deviation before with how we've done expected value here. So let's just go ahead and look at an example of this. This isn't too terribly exciting. I'm more excited about the section 4.3 stuff here today. So let's go ahead and look at an expected value and a standard deviation comparison here so we can see how to compute each of these things. So here's the scenario we're going to take a look at. We want to make a comparison across two things so we can understand how we're interpreting expected value and how we're interpreting standard deviation. We want to compare expected value and standard deviation associated with the rolls of these two different dice. So one of the dice that we'll look at is a fair die, meaning all of the sides are equally likely to be rolled. This is a traditional die, right? The whole point of a die is an equally likely outcome of all sides. On the other hand, I'm assuming most of us are aware of the concept of there being like a loaded die, where it's an unfair die, a die that could be used to cheat in games. Very typically, loaded dice will favor rolls of 6. Lots of games just have wins associated with larger numbers. It's also typically the case that on most dice, the opposite sides of the die, each of the two pairs of opposite sides will always add to 7. So it's in most dice, opposite of 6 is a 1. So here I've given some percentages. These are based on relatively typical results for a loaded die, where 6 is by far the most common. So we're seeing here 91% of our rolls are going to be 6s. Only 1% of our rolls are 1, and we're going to get 2% of our rolls each associated with rolls of 2 through 5. Notice here, in one sense, I just sort of picked these numbers to make things add up to 100%. But really, in general, it is the case that if 6s are much more common because the die is perhaps weighted, then the weight is on the side of the 1 because we want the 1 to be face down so that the 6 is face up. That means that we've rolled a 6. So it is typically the case that if you use a weighting method to load dice, this is also, by the way, a dumb thing I've screwed around with other math professors trying to actually make loaded dice. There's lots of technique for this, like drilling out part of the die to make it lighter, or drilling out part of the die and then filling it with something heavier so that it's a heavier side, or melting the dice slightly in the oven so that when they melt, they're like a little bit heavier on the bottom or something like that. And again, typically, if you want to make 6 be the more common roll, then what you want to do is put all the weight on the one side. Yeah, baking them is like literally how you make loaded dice right there, which is pretty interesting. So if 6 is more common, then 1 should sort of be the least common, and then all the other numbers are only going to come up periodically right there, the 2 through 5s, right? Slightly more often, but kind of unlikely here. So again, what we're going to do is just compare these. Let's go ahead and compute our expected value and our standard deviation for the rolls associated with each of these two dice and compare them, all right? So we already did this yesterday for the fair die. We looked at the probability distribution. We looked at its expected value. I even say it right here. We did this one last video right here. We didn't do the loaded die though, so we'll see some new information right here, and then we'll compute the standard deviation associated with the fair die and the loaded die. We want to kind of make guesses as to how these are going to, what we're going to see as our results here. So in each case, the values that our rolls are going to take on. No, have I lost my keyboard today? Awesome. All right. Okay, I'm not allowed to use my keyboard now. That's good. All right, so the numbers that we can roll here, I'll write all this stuff in. A 1, a 2, a 3, a 4, a 5, and a 6. These are the 6 possible outcomes. And what we know is that with a fair die, we have an equally likely chance of any of those outcomes. So since there are 6 equally likely outcomes, there is a 1/6 chance that any of those will get drawn. In this case, it's easier for me to make a fraction because 1/6 isn't a super nice decimal. It's an infinitely repeating decimal out there. So in this case, I think the fraction version is better. Notice over here for the loaded die, I'm just trying to use a different variable. I'm just calling this y because I just don't want there to be confusion with x. If I'm comparing two things, don't name them the same variable name, right? These are just arbitrary names here. I'm just trying to make a separation here, a distinction between the two. So it's still the case that y is going to take on 1, 2, 3, 4, 5, and 6, but it's going to occur with a different distribution, different number of times over a total number of rolls. So the information I've given, I was told here I'm going to roll a 6 91% of the time. So I'll put a 0.91 as the probability that's associated with rolling a 6. We're going to have a 1% chance of rolling a 1, so there's my 1% chance. And we're going to have a 2% chance each of 2 through 5. All right, and if you notice here, we can add these up to double check that these do confirm for us that these are a probability distribution. We can see that all the probabilities are between 0 and 1, which is good. And if you add them all up, you get 1. Again, all the probabilities are between 0 and 1. And if you add these numbers up, you get 1. 91, 93, 95, 97, 99, and 1 makes 100%. So we've accounted for all possible scenarios here with these two distributions. And so what we want to do is look at the expected value and the standard deviation associated with each of these probability distributions for these dice. We saw last time exactly what we were going to get here. Our expected value here, maybe I'll say our expected value for x here. We did this, we had the value of 1 times the probability of 1/6. Value of 2, probability of 1/6. Value of 3, probability of 1/6. And we added up all these guys here. We saw these were all fractions, the denominator of 6. If you add up 1, 2, 3, 4, 5, 6, you're going to get 6, and 6 is 12, plus 9 is 21. And that gave us 21 over 6, which was 3.5. We want to remember that even though 3.5 is not a possible single roll, it is the average of lots of rolls. If the law of large numbers is allowed to take effect with a large number of rolls being performed, then on average, we should expect to see the average value of all of our rolls being about 3.5, because it's sort of in the middle. Now, what I'm expecting over here is to see an expected value that's not very close to 3.5. If I were to roll this die many, many, many times, my average roll would probably not be this low. What seems to me to be the case is that most of our rolls, more than 90% of our rolls, are going to be a 6, right? So I'm expecting my expected value here to be much, much closer to 6 than 3.5 is, because we're trying to get a sense of what is our average roll. We are very rarely going to roll a 1. We are very rarely going to roll 2 through 5, but we're going to get lots and lots and lots of 6s when we roll this die. So I'm expecting to get a much larger expected value than 3.5. So maybe I'll notate this as expected value associated with y. And we can do the same thing. The only difference is that over here I used fractions for my probabilities, and now I have decimals for my probabilities. The only thing that's really changing. We have the value of 1 times the probability of getting a 1. The value of 2 times the probability of a 2. Value of 3 times the probability of getting a 3. 4 and the probability of a 4. 5 and the probability of a 5. And a 6 and the huge probability of getting a 6. So if we add these guys up right here, then we are going to see, and let me just reference what I feel like I already did this one here. Did not write that one down for myself. That's okay. I can go to my calculator here, and now I'm really going crazy. There we go. Go to my calculator here, add all these guys up. I'm going to do a little bit of multiplication in my head here. The first term is a 0.01. The second term is a 0.04. The next term is a 0.06. Next term is a 0.08. Next term is a 0.10. And then I don't know what 6 times 0.91 is, but I can add that as well. And what I'm getting is 5.75 is my expected value here. So we're seeing, in a sense, exactly what we expected to see. Again, it's not like I can ever roll a 5.75 on a die, but if I were to roll this die over and over and over and over and over again and average up all of the rolls that I got, it makes a bunch of sense that we're getting a number that's incredibly close to 6, but a little bit less than 6, because we will occasionally get some of these smaller values that are out here. So I think this makes a ton of sense to me for both of these guys, right? 3.5 sits exactly in the middle of 3 and 4, and that's a good place for it to be since everything was equally likely. So we went exactly in the middle. Over here, everything was very much not equally likely. I would call this a left-tailed distribution or a left-skewed distribution, since the tail of our distribution is the small values. The bulk of our distribution is to the right. And here, because 6 was super common, our expected value is very, very, very close to 6. So I think that these are sensible to me. These make sense to me why we're getting these types of responses. So coming up with our fair die standard deviation, as we've seen with our previous standard deviation computations, it's definitely a little bit hairier. These are the only ones that I'm going to really do by hand here. And in fact, I've already pre-computed the answers once I write out my work right here, because these are a little bit grosser to do, as we've seen. Fortunately, this class is not going to be about you guys doing standard deviation by hand all the time, but it is worth it to see this computation here. So when we're computing our standard deviation, we want to do the very, very similar thing that we did before. We want to ask ourselves, how much do each of our outcomes deviate from the mean? Since we don't want our positive deviations and our negative deviations to cancel, we want all of our deviations to be a positive amount. So even if it's above or below, we want those to not, in a sense, cancel with a positive deviation and negative one. So we want all of our deviations to be represented as positive numbers. And it's often the case that we want our things that are far away to have more influence when we talk standard deviation. And so squaring the difference between our outcome and the mean is still going to be part of this. We are then, instead of dividing by the n or the n minus 1 as we've done in the past, just like we see here, sort of like multiplying by the probability of occurrence, multiplying by that 1/6 in this case right here. That's sort of our equivalent of saying add up all the rolls and divide by the number of rolls that you had. It's doing that proportionality part for us there. And so very similar in our standard deviation computation before, we divided by that n minus 1. But here, dividing by n minus 1 is really getting the proportionality for us, but that will be built in by just multiplying by the probability of each occurrence here. So what we're going to get here, and again, these numbers are really important. We can't compute standard deviation without having computed expected value, or mean, first. So for our first one here, we want to add up all the squares of the deviations of each outcome from the mean, and then multiply it by the proportion of outcomes that are associated with that. So here's what that looks like. Our first possible outcome is a 1. We can measure how far 1 is away from the average. We don't want this to be counted as positives or negatives or anything like that, and we want things that are far away to be having a little bit more influence, so we'll square this just like we've done before. And then we want to say, and 1/6 of our responses are going to contribute that much to our deviation. And so what we can do is we can just add up these terms for all of our different x values here. So hopefully this feels to you like a perfect combination of how we've done expected value last video and how we did standard deviation last week. It's still the difference squared, and we're still adding them all up, but rather than dividing by the number of trials, we don't have a number of trials, but we do have a proportion of trials in which we expect to see that certain result. So the important thing I want to do real quick before I actually get this right here, so I'll say here standard deviation associated with x, is that I kind of want to compare what I'm expecting to get for my answers here. So let me kind of step away from the things that I just wrote here and scroll back up real quick. when we're talking about standard deviation, we're talking about on average, how spread out do we expect all of our responses to be if we do this a lot? And what I kind of want to ask you is, which of these two dice do we expect to see have a larger standard deviation? In the first die here, we're seeing that there's an equally likely chance of rolling anything, right? So what that means to me is we're just as likely to be far away from our average with ones and sixes as we are to be near to our average, threes and fours. On the other hand, over here, with all of these rolls over here, it seems like we're just mostly going to roll a bunch of sixes, right? So if standard deviation is saying on average, how far is the average roll from the average? Well, our average is super close to six, and most of our rolls are going to be a six. So what I'm seeing here is most of our rolls in the second die are going to be super close to the average roll. So there's not going to be a huge deviation from the mean for most of the rolls with this second die. So what I'm anticipating that we're going to get for our responses for the fair die and loaded die standard deviations is a kind of, and again, comparing the absolute size of these, it's hard for me to eyeball this and be like, oh, I think the standard deviation is going to be about 4. It's hard for me to come up with a number, but I certainly can look at two different distributions and say which one I think is going to be bigger than the other. So I think comparative standard deviations is a really good thing to think about here. So I'm expecting to get some moderate level of standard deviation here for this fair die because all of our numbers are, all of our chances are equally spread out across all possible outcomes here. And so if you go to your calculator and do this one, I did this earlier just because it's pretty obnoxious as you guys have learned to throw this stuff all into your calculator. So I pre-computed my answers here today. 2.917 is what I was identifying for our standard deviation term here. Oh, and actually, it just occurred to me that I actually believe that the answer, I'll go ahead and undo this box here. When you add up all these terms here, what you are going to really need to do is still take this square root of the entire thing. And I'm just realizing I definitely forgot to do that when I was working in my calculator earlier. So that 2.917, yep, I totally did. Okay, that's good to know. 17, and we want to take the square root of that guy. So I'm actually saying 1.708. This term that's under the square root we would call the variance, but we're going to see this semester it's going to be much more helpful to us. By chapter 5, we're going to see a very, very good reason why we care to reference the standard deviation instead of the variance, because the normal distribution is very dependent on the standard deviation, in particular the square root of the variance right there. So in a sense, those two are pretty interchangeable. You can usually get equivalent information from each of them. But the normal distribution will have the strong preference for use of the standard deviation. So we sort of develop that preference now, even though there's not a hard reason to care about standard deviation versus variance in this setting right here. We will come to prefer the standard deviation there. So very similarly over here for the loaded die, I'm expecting to get something smaller than these for the variance and for the standard deviation here. So again, my outcome of 1 is pretty far from 5.75, right? So that's going to make a pretty big contribution overall to the variance or standard deviation, except for the fact that it doesn't occur very often, right? So in a sense, this is a big deviation, but it only represents a very small portion of the deviations that we're going to see. Only 1% of them are going to deviate with this sort of contribution to that term there. 2 minus 5.75 squared times 0.02. So this is not quite as far of a deviation, but it is twice as likely as the last one over here. So that'll make, again, a pretty small contribution. This has even less contribution because 3 is even less far from the mean, and it still doesn't occur very often. 4 is even less far from the mean, so it's going to give an even smaller contribution. 5, we're almost sitting on the mean by now. It still only occurs 0.02 or 2% of the time, 0.02. And finally, you should notice that this last term right here is super duper close to the average. So you should notice that this number here is going to be a really small number, but it represents 91% of all of the outcomes that we actually get here. So this has the biggest deviation, but I'm not sort of circling this whole term with my cursor here, right? Just the deviation part. The proportion of them that experience this amount of deviation is very small. So on the one hand, this first term is big. The first part of the first term is big, but the second part of the first term is very small. So this will be a pretty small amount of deviation overall. On the other hand, over here, the deviation that 6 is away from 5.75 is very, very small, but it occurs a lot of the time out there. So we can think about what the individual contribution is to the overall standard deviation for each of these guys based on how far away was that and how often did we see stuff that was like that. So when we go to our calculator, again, I think I failed to do my square root step at the end here. So let me just stop even writing standard deviation. Okay, I got to stop crossing out and use my backspace here more. So my variance, then, if I go ahead and add up all that stuff, right, go to my calculator and do that somewhat obnoxious computation here, I'm getting 0.7875. And if I take the square root of the variance, then I get the standard deviation. And I can take the square root of 0.7875, and that's going to be 0.887. So the good news is that this exactly matches my intuition that I had going into this problem. What I was thinking to myself is that the rolls that I get from the fair die do deviate from the mean just as likely as not really deviating from the mean, right? Getting a 1 or 6 was, which is far from the mean, is just as likely as getting a 3 or 4, which is close to the mean. There was a big spread in our responses that we were going to see. In our second scenario, here is a much smaller spread of responses. We don't get as much deviation from the mean as normal because, or as when I say as normal, I mean as with a fair die, because most of our rolls are very close to the average. So we got a much smaller standard deviation in all of our responses. Each response on average deviates from the mean of 5.75 much, much less than the average roll of a fair die deviates from the average of 3.5. So we can make comparisons across these standard deviations now to say we get much more consistent responses over here. There's less deviation. We get a broader spread of responses here. There's more deviation from the mean. So there's our standard deviation computations. I don't ever want us to deal with the standard deviation of a discrete random variable with more than 6 things right here. This was annoying enough for me to do this in my calculator. I'm not looking to crush us with obnoxious calculator stuff right here, but it's good to see where these come from, to think about the individual term contribution in each of these parts right here, and to make comparisons across standard deviations of things with different distributions. So here's our good example right here. We are given in words what the die do. We wrote that out into tables to describe their probability distributions. We used the tables to help us compute the expected values, and then we used the expected values to help us compute standard deviations. And we made guesses before we did it, and our comparative guesses were good. As I said, it's really hard for us to be like, oh, I think the standard deviation is going to be like 1.3. Guessing a number for standard deviation is always difficult for me, but it is generally easy for me to say, I think this data, or excuse me, this particular type of event is going to have a larger standard deviation than this type of event or experiment or something like that. So comparatively, it's, I think, good for us to make those comparisons there. So that's all I had to wrap up 4.2 right there. I just didn't want to go obviously it's a lot of writing on the screen right here, which I didn't want to dig into in our when we were an hour and a half in yesterday or whatever that was. So there's our wrap up to 4.2, getting some comparisons of some standard deviation computations. And just remember, like I did, technically at the end of this addition, you then take a square root because we added up a bunch of squared terms. We then square root it. In a sense, we grew it with the squares, and we want to undo that with the squaring. It's not perfectly algebraically consistent right there, but it does the job that we're looking for here. So variance and standard deviation are both useful for the same idea, but again, we're going to have a strong preference for the standard deviation for the whole second half of the semester here for lots of computations. So remember, if you're ever computing this, that this was really our variance here. Let me just do this so that my notes actually look more correct right there. That's our standard deviation. The variance is the term under the square root there. Okay, so there we go. There's our wrap up to 4.2. So what we now want to do is hop into 4.3, the binomial distribution. This is the thing I'm actually maybe a little bit more excited to talk about today. I just think this is a little bit more interesting. Getting into the discussion of our distributions of interest this semester is I don't. I gotta say, the beginning of teaching stats is always. I struggle with making it exciting the first few weeks of this class. I'm assuming most of you guys have felt that. We are now arriving at all of the interesting topics. I think things like the expected values that we computed last video for like gambling and health insurance are very interesting questions. I think discussing our special distributions that we're starting with binomial distribution, I think are very interesting. There's actually interesting questions to answer that we can't just directly just intuit the answer like we think about dice rolls and flipping coins and stuff. So we're, in my opinion, this is sort of where we're like kind of finally getting to the good stuff right here. So I hope that you guys kind of feel the same way here. So let's kind of define what we mean about this binomial distribution and see some computations associated with it. The outcomes of a binomial experiment will follow a binomial distribution. So that's just sort of a sentence right there to get you comfortable with sort of like how we use these words here. Some statistical experiments are binomial, meaning, what does it mean to be a binomial experiment? It means that you have a fixed number of trials. This isn't like play this game until you win, right? That would not be a binomially distributed experiment because in that case, I don't know how many games I'm going to play, right? If it's play until you win, there is a non-fixed number of trials. On the other hand, if I said we are going to check and see if it rains for 20 days, then I know that there are 20 trials. It rained or it didn't on 20 days, right? So a fixed number of trials, and again, the letter N will represent the number of trials, the sample size for this entire semester. That never changes. There are only two possible outcomes. The bi in binomial is indicating that there are only two possible results for every single experiment. So this is very much the exact opposite of things like how tall are you? How tall are you has in a sense an infinite number of responses depending on how finely you can measure your height. On the other hand, for the binomial experiments, we're looking to get just successes and failures. It rained today or it didn't. You're a male or you're a female. You have cancer, you don't have cancer. There can't be a third choice. In that case, we're not talking about binomial distribution stuff, right? So only two possible outcomes. We generally define these to be success and failure. But I brought this up, I think, like 2 weeks ago. Success and failure here are very, very much statistical words and not like people words. And by that, what I mean is if you're a cancer researcher trying to identify if people have cancer or not, you'll probably label it as a success if you find and identify a person that does have cancer because that is a positive result. They tested positive for cancer. That is a success statistically. Obviously, that is a failure in a life sense if you have cancer. So just kind of remember here, success and failure are defined in an academic sense here, not like, was that good for you or not? It's like, was the answer yes to your question? Yes, they have cancer. That's defined as a success versus a failure. So in general, we use the letter P to define the probability of success and Q to define the probability of failure. Since the only thing that can happen is success or failure, that has to represent all 100% of the possible outcomes. So the probability of success plus the probability of failure is 100%. This sentence says to me, there is a 100% chance that you either have cancer or that you don't. All right? This is a pretty simple algebra statement right here, but I think people get lost in like interpreting it, even though it's an easy equation. If there's only two outcomes, then there's a 100% chance that you either got the first outcome or the second outcome. That's what we're saying right here. Finally, what needs to be the case in a binomial distribution is that every single trial is identical to all other trials and that all trials are independent of one another. So a really important thing here is that even if we are looking at, maybe we're playing a game with a deck of cards and the game is only based on whether you draw a red card or a blue card. There's 52 trials if we're drawing every card in the deck, so we wouldn't know exactly how many trials we're performing. There are only two possible outcomes. You're drawing a red card or a black card. But if you are not putting the cards back in the deck, then every card that you draw is going to influence the probability of the future draw's probability of being red or black. And in that case, those probabilities are no longer independent. Each future draw that you make, the probability of drawing a red or black is dependent on what you have previously drawn. So realize that this comes back now to our whole with replacement, without replacement for some types of trials here. If we weren't putting cards back in the deck, then even if there's only two outcomes, red or black, And even if we know how many trials we're doing, this still wouldn't be a binomial distributed thing that we could discuss here, because in the case of keeping the cards out of the deck, we no longer have independent and identical trials, because now the probability of red and black had changed because we've removed cards from the deck. However, if we were putting the cards back in the deck with replacement, then every trial is the same. There's a 50-50 chance of red or blue, and we could do any number of fixed trials right there. So this is really important that every single trial is the exact same as all other trials, and that the result of one trial never influences the probabilities associated with future trials. So these are sort of the rules. If you pass all three of these tests right here, if you agree with all three of these rules, then the experiment that you're performing is known as a binomial experiment, and the results of your experiment will follow what we call a binomial distribution. So since this is a probability distribution for a variable, it's very typical that we want to identify what are the mean and the standard deviations that are associated with that given variable. So let's go ahead and look at this. One of these is sort of obvious, one of them is not. And so let's set up some formulas for these guys. So suppose that 30% of the citizens of a town smoke cigarettes. If I go out and poll 50 people, then how many do I expect to find smoke cigarettes? And notice I just emphasized a word expect that I don't have written right here. Remember that average and mean and expected value are all the same thing. So in this case, I think it's easier for me to think if I perform this experiment one time, I think it's easier for me to use the word expected value to think about this. How many people do I expect to say, yes, I smoke cigarettes in this if I did this once? On the other hand, I think if you want to think about this as mean or average, I think that the other phrasing I like to use for this scenario is, suppose that I assigned like all 70 of my statistics students to all go out and poll 50 people and ask if they smoke cigarettes. All 70 of you are going to find some number. Some of you are going to find 13 people. Some are going to get 21 people. Some are going to get 18 people, right? And all of you are going to come back to me and report the number of people that said yes. We could then average all 70 of your responses that were from 50 people each, and what we would expect to get would be that average value of responses right here. Hopefully you guys can see that this is a pretty easy computation to do. What I'm expecting to see here is I'm expecting to get 30% of the 50 people that I poll to say yes. So my expected value in this case right here is just the 30% of the 50 people that I polled. And in that case, I would say 15 people. That's how many I would expect to get. The average response, if we did this trial over and over and over and over again, would probably be 15 people. Individually, if all of you as students went out and polled 50 people, most of you probably wouldn't get exactly 15. But if we averaged all of our responses, the collective class average would probably be very close to 15. And notice that the computation that I did right here, and by the way, remember this symbol mu is our average. Average, expected value, mu, mean, these are all the same thing. All we did here is we multiplied the probability of a success. And again, I don't exactly consider being a cigarette smoker to be a success. No offense if you do, I don't care at all. But again, statistically, we define this to be a success. We found a person that does the thing of interest. And then we multiplied by the number of people that we were sampling. I guess this is typically more often written as NP instead of PN right there, but it doesn't matter. We can compute the average of a binomially distributed variable by multiplying the number of people being sampled times the probability of experiencing a success. Very easy computation right there. So our formulas for the mean and for the standard deviation, we are seeing, I just wrote it right there, our mean we denote as mu. It's the U with the tail on it. And in general, this is just written as NP. N is the sample size, P is the probability of success. Our standard deviation is less obvious for a formula, but I'm going to give you the formula, and then we'll look at it and convince ourselves that it's giving us answers that make sense to us. So we've also seen our notation for standard deviation is another little Greek letter there. It's our sigma. All my sigmas will always look slightly different. You will learn to identify them. And this guy is going to be, as we've seen before, it is the square root of something. The variance is just the unsquare rooted version. And this will pretty simply be NPQ. And remember here that since P plus Q is 1, I can just do some real simple algebra here and say that Q is 1 minus P. So it's also the case that you could write this as the square root of N times P times 1 minus P would be an equivalent version of that guy right there. And that's just for making that little swap based on our definition of P and Q. But it's typically written this way right here. So these are our formulas to compute the mean and standard deviation of a random variable that is binomially distributed. But that standard deviation, I hate just giving people stuff and being like, there's the formula. Unfortunately, where this one comes from, as with many things, is a little bit hairy, but we do want to stop and convince ourselves that this makes sense. So let's compute a couple standard deviations and see why we agree with the results that we're going to get here. So let's check that the standard deviation formula makes sense for two different scenarios right here. We want to, again, let's do a comparative standard deviation here to see if it makes sense. So let's determine the standard deviation associated with the number of heads observed when flipping a coin 500 times. So in this case right here, I'm going to perform the experiment 500 times. 500 is my sample size. In this case here, my success is a heads. The probability of success is 50% because 50% of the times I'm going to get heads, 50% is tails. The probability of a failure of getting tails in this case should always be 1 minus the probability of success. And obviously we all know that there's equally likely chance of getting heads and getting tails here. So we could compute our standard deviation then as the square root of 500 times 0.5 times 0.5. And I'm going to go to my calculator and do this. 500, and really we're getting 1/4 of 500, so it should just be the square root of 125. I'm going to take the square root of 125. What am I getting here? 11.18. Now it's really hard for us to interpret what this 11.818 means, but here's kind of the thing that I'm thinking. If you flip a coin 500 times, you should expect to get about 250 heads. But I don't think it would be very weird for us to get even 220 heads or 280 heads, right? 220 and 280 are 30 above and 30 below the expected number of heads for us to get out there. And I don't think that's wildly incorrect. I think it wouldn't be weird at all for you to get, and in a sense that would be like getting 22 out of 50 heads. That seems kind of perfectly reasonable to me that might happen. So what this is saying to me is that our standard deviation here being 11.18, one of the statements that we're going to end up making next chapter is that about 95% of all of our results in general will always fall within 2 standard deviations of the mean. So that says if all of you guys, all 70 of my stat students flipped a coin 500 times and reported back to me the number of heads that you got, we would expect 95% of all of you to have gotten about 22, to be getting a number of heads in the range of 22 heads less than 250 and 22 heads more. And 22 here is my 2 times my standard deviation. And that seems ballpark reasonable to me. We got a lot of math to do to sort of justify that statement that I just made. But the point here to me is I'm expecting to see, I think it's not unusual to see a decent amount of variability in our responses right here. If one person got 220 heads and one person got 280 heads, I don't think that's that weird as far as flipping a coin goes 500 times out there. Those both seem to make sense to me. So there's a moderate amount of deviation that we're expecting to see in our results across 500 coin flips. Let's compare this now to a different scenario. So the important thing that you should notice here is that my P and Q were the same. This is as close to the middle as they could ever get. Exactly 50-50 chance right here. It couldn't be more evenly distributed. The comparison that I'm trying to make now is sort of the opposite scenario. 1%, at least as far as whole number percentages go, is sort of as far away as I can get to an equal 50-50 split. Again, I could make this like a 0.01% and it would be even further away right here. I'm just trying to use reasonable numbers right here. So in this case, now I'm saying, suppose that 1% of all people in the US either currently have or have had in the past a cancer diagnosis. What I want to know is what is the standard deviation of responses if we poll 500 people and ask, hey, do you currently have cancer or have you previously had a cancer diagnosis? So again, in this case, I'm going to keep on emphasizing here that a success is very much a statistical definition here. So in this case, success equals cancer. That's the craziest thing I think I've ever written in my life. Success equals cancer, but that's our statistical definition here. We have 500 people that we're sampling. That's our sample size. Our probability of success, our probability of observing a person that does have or has had cancer, 1%. Therefore, our probability of a failure should be the other part, the complement of this, the other part out of 100%, which in this case is 99% right there. So we could go ahead and compute our standard deviation then as 500 times 0.01, there's my P, times 0.99, there's my Q. And in this case here now, I'm going to get, let's see, 500 times 0.01 times 0.99. And that's going to be 4.95 underneath the square root. And I can take the square root of this guy. 2.22. So what we're noticing here is we got a much, much, much smaller standard deviation. And hopefully that makes a ton of sense to you. The reason why this makes sense to me is because if all of us go do this poll, right? If all of us went out and every one of my 70 stats students asked 500 people, hey, do you currently or have you in the past had cancer? Then what we should all expect is if only 1% of people should be expected to respond yes, then out of the 500 people you poll, you should only expect to get about 5 yeses and 495 no's. There's not a lot of deviation in your responses. You're pretty much just expecting to see almost everybody say no. That's not a lot of deviation. There's only a small couple rare people that are going to say yes. That's your sort of deviation from the normal response right there. So here we're seeing much, much, much smaller deviation. Standard deviation because our responses don't vary as much. Here, this is like the most variability that we ever could have accumulated right here. And so notice that this P times Q is sort of really what's driving the size of this thing. I on purpose kept our sample size the same here. So kind of notice that I'll kind of put this in red right here. 0.5 times 0.5 is 0.25. That's literally as big as P times Q could ever be, ever. Because the closest we could ever get to an even spread of likelihoods is a 50-50, and 50% times 50% is always going to be that 0.25 is a number right there. On the other hand, down here, this is saying take 0.99 and shuffle the decimal over 2 places. This is a 0.0099. That's a much, much, much smaller number there when we're comparing a 1% chance to a 99% chance. And so in a sense, these are sort of the numbers that are guiding the overall size of our standard deviation in those cases right there. So this is sort of saying to me a 50-50 probability is the greatest amount of standard deviation we could have. And when we get very close to these extremes where we have 1%ers and 99%ers, this is when we're going to get very, very small standard deviations because we don't experience much deviation in our responses. Pretty much all the responses are no, I don't have cancer and I've never had cancer. It's mostly all of our responses, right? So computing these is pretty easy. It's not super obvious to use this formula necessarily, but given to you, it's pretty easy to use. This is, by the way, just appreciate how nice and easy this is rather than doing those computations that we did above, adding the squares and square rooting, all that crap. This is pretty easy. You do a little multiplication, you take a square root, and you're good to go. So again, I am interested in you guys comparing standard deviations. I think that this is probably the question that I'm more likely to ask you like on next week's test is to say, which of these variables do we expect to experience a broader spread of results? And you're going to compute 2 standard deviations and say, oh, it looks like this one has a broader spread of results, stuff like that. So there's our computation of our basic statistics, mean and standard deviation. Those are things that we always are interested in for every distribution. Other things that we're interested in that we'll be doing for every distribution is notating that distribution. How do I describe this without having to write a whole 2-line sentence? That's just, no mathematician on earth wants to write out crap like that every single time they have to indicate a piece of information. So you should notice that to define a binomial experiment, we need to know how many trials we're performing, and we need to know the success of each trial. You should also notice that Q comes up in every single one of these computations that we're doing, but I can always determine Q just by knowing what P was. It's always just 1 minus P. So that's not really extra information. It's useful, but they're not, like I'm not given more information. Like if I know that P is 1%, I by default know that Q is 99%. That doesn't need to be like given to me. So as long as I know N and I know P, I know everything I need to know about how this variable is distributed. So N and P are really the key here. So this is standard type of notation that we'll use all semester. The random variable x, there's the random variable x. In fact, what I'm going to kind of do here is try and like box off this stuff. The random variable x, that's my first part, is distributed according to, we use the little tilde symbol right there to indicate that the variable is distributed according to something. Rather than like an equal sign saying it's the same as something, the tilde, the twiddle, is indicating is distributed according to a binomial distribution. We need a little symbol that says the binomial distribution, not the uniform distribution, not the normal distribution, but the binomial distribution. Typically, this is written as just a capital B. I do see other places where it's given as like bin right there. You can do either, that's fine, but that's just our little shorthand for the binomial distribution. And then we've got with n trials of probability of success, with n trials, and a probability of success on each trial of p. And all we're going to do after the bin is put np right there. So those are sort of my 5 parts to this right there. So reading each of these 5 chunks, the random variable x is distributed according to the binomial distribution with a number of trials n and a probability of success p. So it might be the case to you that I'm going to say, hey, tell me the average of the variable x. And I might just say to you, oh my gosh, I'm typoing all over the place right here. Write this correctly, dang it. See, I even tried to write an equal sign right there. So I might just say to you, tell me the average, and just give you this. You need to know that this 12 is representing the sample size and that this 0.3 is representing the probability of success. It will always, I will never mix this order up. It's always NP. NP, as I said above here, I regretted even setting up this multiplication the way that I did in this problem because it came out to be P times N. I just think of this as 30% of 50 people, so it verbalizes to me better as PN. But the average is N times P, NP. NP is what you got to know for the binomial stuff right there. So it'll always be in this order. So I will, in the future, give you phrasings that look like this, and you will say, okay, I know I'm thinking binomial distribution stuff. We're going to do 12 trials. There's a 30% success, 30% chance of success on any one given trial right there. So that's how we sort of notate this nice big long sentence right there so that we don't have to write or read those sentences anymore. So let's get into the cool stuff here. Let's compute some actually interesting values that are associated with this binomial distribution. And I know I'm going to need a little bit more room here. So this is one of those things where we are going to want to use a calculator to do this for us. But the motivation to use Excel or a calculator generally comes from doing it by hand and realizing that that's not going to be doable. So let's do one by hand that is doable. See how it's going to work, see what part of it's going to be a real pain for us to do by hand in the future. Then we'll pop into Excel and see how Excel handles a bunch of this really easily for us. So suppose that the probability of rain on any given day in January is 70%. What is the probability that it will rain exactly 2 out of 5 days? We're going to do this by hand, but we're going to do this in Excel, or you can get this figured out in a TI calculator as well. In our textbook, they show you exactly the button presses for the TI calculator. So the first thing we need to do is verify that this is a binomial experiment. So remember the 3 rules that we came up with is that there are exactly a fixed number of trials. We're doing exactly 5 trials. So I'm going to say exactly n equals 5 trials. There are 5 days over which we're going to say, did it rain or not? It is the case that there is a probability of success of P equals 0.7 on any one given day. And finally, the thing that's really important about this one here is we are assuming that the weather of any day is independent of any other day. So what that means here is we're making the assumption here, if we want to use the binomial distribution, we have to assume that, for example, Just because it's raining today does not necessarily give us a greater probability that it's raining tomorrow, which may or may not be the case. And what I can even tell you is that whether or not that's actually true is regionally dependent, and it is also seasonally dependent. In some seasons of the year, rain on one day is more likely to indicate rain on another day, and in other seasons of the year, it's more typical to have like scattered showers rather than storm systems, stuff like that. So I'm going to say right here uh, that this is only maybe true, but we can't do any computation if it's not true. And so one of our jobs as statisticians is always to say, listen, here's the criteria that have to be met for computation to make any sense, and for you to make an argument that all the criteria have or haven't been met. It might be the case that you cannot guarantee independence of trials, but that maybe you're like, I'm pretty sure that most of the time it's independent. We're still going to do the computation. We just know that there might be some error in our results more than we expect, based on the fact that maybe our trials weren't quite as independent as we thought of each other. But again, what would we do? Just never even attempt to make a computation? So in a lot of things in statistics, it's the case where there's sort of like a list of criteria that need to be met for a computation to be valid. And it is regularly a statistician's case to make an argument that those have been met in a sort of objective sense. It's hard to prove that weather on any one day is independent of weather on any other day. It's a hard thing to prove. That's a whole stats project in itself right there. So sometimes we're more making an assumption and then possibly at the end saying, and listen, our answer here might be a little bit off. It might be a little high. It might be a little bit low because maybe that one assumption was not actually quite as firm as we wanted it to be. But it's better to just say that and place a modifier on your results rather than just be like, well, there's no point in computing this. Like, we still want to get an estimate here at least. So here's the deal. What I'm thinking to myself is this. If I'm going to do so these are my justifications that it's legitimate for me to even think of this as being binomial distributed because we agree with our 3 requirements for the binomial experiment. So my thing that I want to do here is I want to say to myself, well, how might this happen? Well, I'm kind of thinking to myself, we need to do, this is always going to be a 5-day experiment, right? So I'm going to give myself 5 little slots right there to think about a probability. One way that this might go down, that we see this happen, is we might see that there's going to be rain, rain, and then no rain, no rain, no rain. That might be how our 5-day check goes. If things go down like this, then that means that there was a 70% chance of that event occurring on Monday, and, meaning due multiplication, a 70% chance of that event occurring on Tuesday, of the rain event on Tuesday. Then we would have 30% chances each on Wednesday, Thursday, Friday of seeing no rain. This would be one way in which we could get a success associated with this guy right here. And notice that I can more simply write this as 0.7 squared times 0.3 cubed. Notice that this is the probability of success to the power of the number of successes times the probability of failure to the power of the number of failures right here. And this is good. We're very close to actually just, in a sense, already being done with answering this question. But here's my issue. So far, what I've worked out is only one of the possible ways that we could get rain 2 out of 5 days. The one that I've got, I'm thinking of this as just like Monday through Friday to like help me verbalize this here. The version that I did was just the version where rain happens on Monday and Tuesday, but not Wednesday, Thursday, Friday. So here's the thing I'm thinking. There's a bunch of different ways this could have happened. So here's my words that I want to use. In between each of these days, I use the word and. We wanted rain on Monday, and rain on Tuesday, and no rain Wednesday, and no rain Thursday, and no rain Friday for this to achieve what we were hoping to see, 2 out of 5 days. All of those words were and in between, so we did multiplication between each of these groupings. But overall, this grouping, this week, this 5-day week right here is one of many possible ways that that could have happened. It could be that we had rain on Monday and Tuesday as our 2 days of rain, or it could be that we had rain on Monday and Wednesday as our 2 days, or Monday and Thursday, or Monday and Friday. And what we remember from last week is that the word or says do addition between each of your possible results. So maybe the next case that we might want to think about, our next 5-day scenario here, is that we could have rain on Monday and rain on Wednesday, no rain Tuesday, no rain Thursday, no rain Friday. These are associated with 70% chance, 30% chance, 70% chance, 30% chance, 30% chance. Now, the interesting thing that you should notice here is that this is still me multiplying 0.7 twice. This is still me multiplying 0.3 three times, because we still had 2 yeses and 3 nos. All right? So it looks like what's going to happen is this. What I need to figure out is all the different combinations of 2 days of rain out of 5 to know how many ways this could occur. And I need to add up this same value. It looks like we're just going to keep on getting 0.7 squared times 0.3 cubed for all of them. It's just different orderings of the 0.7s and the 0.3s. But multiplication can happen in any order. So I'm not getting a different answer, but it is true that there's several different ways that we could do this. So here's what I'm thinking. It should be that our answer times the 0.7 squared times the 0.3 cubed, right? This is the probability for one way of occurring with 2 out of 5 days of rain. We just need to add them all up. How many different ways could there have been rain for 2 out of 5 days? And to add up the same probability multiple times is really just to multiply by that number of ways. So let's sort of make a list here of all the ways that this could occur. And I'm just going to use X's and O's to make this a little bit more simple here. So this is saying Monday and Tuesday are the rain days. Monday and Wednesday are the rain days. Monday and Thursday are the rain days. Monday and Friday are the rain days. That's a whole bunch of different ways it could rain 2 out of 5 days. So these are all my choices, with Monday being the first rain day. I'm just trying to organize my work here so I don't get lost. Now let's look at all the ways that Tuesday could be the first rain day. Well, Wednesday could be the second one. Thursday could be the second one. Friday could be the second one. Those are all the ways that Tuesday could be the first rain day. All the ways that Wednesday could be the first rain day. Well, Thursday could be the second. Or Friday could be the second. And finally, all the ways that Thursday could be the first rain day. Well, then Friday has to be the second one. So it looks like what we're seeing is there is 10 possible ways to choose 2 things from 5 things. In this case, it's days of the week, but it could have been, pull 2 green apples out of a bag of 5 total apples or something like that, right? It could have been anything that's out there. So it seems to me like what I think is happening is I'm adding up 10 different ways that this probability could occur, because it could be any of these ways with an or between them. It could be rain was Monday, Tuesday, or Monday, Wednesday, or Monday, Thursday, or Monday, Friday, or. And those ors are saying add up 10 things. But all 10 of the things I'm adding up are the exact same probability computation. So I'm just going to do 10 times this number right here. And so what I'm thinking I'm going to get for my final answer here is 10 times 0.7 squared times 0.3 cubed. So this is the probability of success times the number of successes times the probability of failure to the power of the number of failures. Did I say power before? I think I just said that wrong. The probability of success to the power of the number of failures times the probability, oh my gosh, sorry, I keep on saying my words terribly here. I'm going to get this right this time, I swear. 0.7 is the probability of success. 2 is the number of successes we want to see. 0.3 is the probability of failure. 3 is the number of failures we want to see. How many ways could we get 2 successes out of 5 total trials? It looks like there's 10 ways to experience 2 successes out of 5 trials total. And so in total, if I go ahead and add all these guys, or if I multiply this guy up in my calculator, 0.7 squared times 0.3 cubed times 10, I am getting 0.1323. Right. And so we can kind of finish off with like a sentence here from our computation. We compute this number out of our calculator, and we interpret that as a 13.23% chance of 2 rain days out of 5. Now, the thing that was easy here was doing this part. The thing that was hard here was counting the number of ways. And this is one of those things that we are not going to spend a whole day talking about the smart way to do this. Oh, hey, analysis right there. You can email me about that. I'm sure that we can work out a way to make that all fine right there, analysis. Why don't you send me an email or a Canvas message and we can make a plan for you right there if you'd like me to open a homework back up or something for you there. So what we want to do is recognize that, again, coming up with this stuff right here was pretty okay, but counting the number of ways was kind of a pain. I had to make a list here, and no problem. And if I had to make this list, if I were to say to you, what's the probability of 70 days of rain out of 100, it would take you literally like your lifetime to make the list of the number of ways. So we want something a little bit smarter here. And so I am going to show you a formula for this, but I'm not really interested in us using the formula. I just feel like I could never teach this if I didn't show you the formula, because that's what a math professor does. I really want us to use Excel or RTI calculators to compute these things for us. So Excel is going to give us this exact same answer here in 1 second. So I want to compare what we just did. I'm scrolled exactly on the screen right now for a reason right here. I want us to see that we did exactly these things. So let me get out my color right here to see that when we compute the probability that our random variable x, which we've defined to be the number of days of rain, to be exactly some number of successes, right? K is our number of successes here. So this is saying what's the probability that our random variable, number of days of rain in 5 days, takes on the value of 2, is what we just did. What we did is we multiplied the number of ways it can occur, 10, which we would compute with this little nk thing right there. That's the thing that I'm going to say to you right now. Hand wave it. I'm going to say, don't worry about this. This is easily something we could talk about. It's just not worth 45 minutes of my time in a lecture video is basically how I feel about that guy. And it's okay, because I'm not going to expect you to do a bunch of these by hand. The second part of our equation is the probability of success times the number of successes. So notice P is the probability of success. K we define to be the number of successes, so that exactly matches. And then we've got the probability of failure to the power of the number of failures. Our probability of failure is the other part out of 100%, so 1 minus P, also known as Q. And also, if we did n trials and K were successes, then n minus K of them, the other ones, must have been the failures. So n minus K is the number of failures. It should be all the rest of the trials, right? Notice that K plus n minus K is just n, because the K terms cancel out, because we had a positive and a negative one. So it's the total number of trials there. So we did exactly what this formula suggests that we should do. We just didn't come up with this term smartly. We made a big old list to get this n choose k. How many ways can you choose k things out of n things? We do have this formula over here. We do get some factorials over here. If you're familiar with those terms right there, great. If not, I don't care, because I'm not going to directly ask you to use this formula by hand. I am going to be more interested in you using technology to compute this amount right here. I just want to show you that what we built naturally agrees with the sort of formal statement about this. Maybe the last thing I'll just say over here is notice that there's this like f of x kind of looking thing right here. If you're familiar from algebra that we use function notation like f of x, f is the name of the function and x is what we plug into it. In this case, we need to plug in more than just one piece of information. I need to know how many successes we expect to see. I need to know the overall number of trials, and I need to know the probability of success on any given trial to be able to compute a probability of success in a binomial situation here. So pretty, maybe a little hairy for notation, but I don't think it's that bad. I think hopefully if you can see why we built this one this way, then you can see that each of these pieces exactly match each of these pieces that we've got for our more formal statement here down below. What I'm a little bit more interested in, as I've been saying, is I'm more interested in hitting up Excel for some of these computations. So let's go ahead and ask Excel to do some nice things for us right here. So what we're going to see in Excel is just like we see sort of this function notation statement right here, where there is a function f and it requires 3 pieces of information to make the computation. We're going to see a function called binomial distribution, and it's going to require us to give it 4 pieces of information right there. And notice that four pieces of information almost exactly match this one, except we've got this one weird word on the end, which we're going to, as I'm going to indicate right here, which we're going to be very careful about right there. It turns out it's an easy one. You're always just going to put in true or false for cumulative, but we'll kind of we'll talk about that one here. That's going to be kind of one of our points of conversation here. So number, and by the way, this is exactly how Excel notates it to you. And an important thing is that when I go to Excel in 1 second here, when I like hover over a cell, Excel is going to show me all this, but the hover over is not going to show up on your screen for me, like from me. But when you go to Excel, you will see the hover over that I'm talking about right here. It just doesn't display out through OBS as I'm using it right here, because I don't know why, because it's a hover over thing. It's like an alt tag for the thing, and those don't show up for me here. So this number of successes, this is successes. This is what we have been calling K up here. This is our number of trials. I don't need to write trials. This is just N. This is our probability of success. Prob of success. That's P. And cumulative is going to say, are you looking for the probability of up to K? This would be like saying, what's the probability of having at least, or excuse me, at most 2 days of rain? So 0 days of rain, 1 day of rain, 2 days of rain. That would be cumulative probability of up to 2. Or do you want the probability of exactly 2? So this is going to either be a true or false. Always. You're never going to put anything else in the cumulative slot other than the word true or false, meaning are we looking at the cumulative probability up to 2 days of rain, or are we looking at, and that would be true because we would be looking at a cumulative probability, or false? It's not cumulative. I just want to know the probability of exactly 2 days of rain. So cumulative will always get a true or a false right there, depending on if we want a probability of an up to amount, or if we want the probability of exactly this amount. That's the cumulative distinction right here. So let's go pop over into Excel and let's do exactly the problem that we just did a minute ago. So let me rearrange this right here. Oh, that was a little funky right here. There we go. There we go. And let me make Excel a little bigger here, although we really don't need all the Excel. So here we go. Okay. So the probability of rain is this exact same problem that we were just doing. I just want to show you that Excel is going to give you the same results right here. So notice, and I'm going to come back over here real quick, the things that we are interested in identifying to give Excel information are the number of successes, K, the number of trials, N, and the probability of success, P. So one of the things that I think is helpful for me in Excel is to literally give myself a K, an N, and a P. So I'm going to say here successes, which I'm going to think of as K. I'm going to think of trials, that's N, and prob of success is going to be P. Oh, I hate that. Get in the middle. And what I'm going to do is I'm just going to give the values of these. I know how many successes I'm looking to see is 2. I know that the number of trials we're doing is 5. And I know that our probability of success is 0.7. So I'm just sort of organizing my information in Excel. And I'm going to show you in a second. You don't need to write out any of this. You can just go straight into the Excel computation. But I think you're actually going to save time by doing this, and I'm going to show you why. So our probability of, and I'm going to say, actually I'm going to form this up the way that I mean to say it. The probability that our variable, random variable x of number of days of rain takes on the value of 2. We can compute this with a binomial probability here. So what I'm going to type in here is kind of exactly what I just showed you in Microsoft Word. And again, as I start to type, what you can't see is there's going to be some stuff like a drop-down thing that's going to pop up that I can see in Excel. It's just not being ported over to the version that you can see. But when you do it in Excel, you will also see the little like helper tags come up, and it is helpful to see them. So I'm going to use that function. Binom dist, and capitalization does not matter here. It always does all caps. I never do that. So binom.dist. As soon as you open a parenthesis, it's going to show you that it wants exactly those 4 pieces of information. I'm looking at a thing that's literally right here. I am hovering over a thing. It is even giving me the finger instead of the cursor because I'm on something. You just can't see it. I'm looking at it right now. So it's telling me number of successes. So where do I have number of successes here? I'm holding my number of successes information in the cell E5. So I'm going to type in E5, and it's highlighted that in blue. It's my number of successes. Comma, I now want my number of trials. I've got that in E6. It's highlighting it in red for me now. Comma, it's telling me now I want the probability of success. I'm holding that information in E7. And finally, it wants to know if this is a cumulative probability. Is this like an up to sort of situation? And the answer is no. We only want to know the probability that we're going to have exactly 2 days out of 5 of rain. So I'm going to say false, which is really sort of my way of saying no. Now when I hit enter, and by the way, before I hit enter, if you don't have an equal sign right here, it doesn't know that it wants Excel to compute something for you. So that equal sign being first has to be there. So now when I hit enter, it's going to give me a probability, and you should notice that it's exactly the number that we just computed by hand a minute ago, that 0.1323 right there. That's our 13.23% chance of rain. Now, I want to point out to you that we could have done this just typing these numbers in directly. I could have just done equals binom.dist. I could have said number of trials was 5, or excuse me, number of successes was 2. Cool, Jazz. I'll come back to it in 1 second right here. Number of successes. So in this case here, again, I kind of got to know what it's expecting me to do. Yeah, Jazz, I'll come back to that in 1 second. So it's always looking for number of successes first. Here, that's 2. Number of trials second. Here, that's 5. Probability of success, 0.7. And is it cumulative? False. In this computation, I am directly entering the numbers 2, 5, and 0.7 rather than referencing them out of this guy right here. But again, I hit enter and it still gives me the correct answer. So what Jazz is asking here, can you see this? I'm kind of guessing not. Wish that was bigger. I don't know if I can make that bigger here. So actually, I guess what I want to do here is this. Here's what I'm going to do. Okay, that's still, oh, okay, there we go. So Jazz, this is exactly what I have entered right here. And notice that my choices for number of successes, number of trials, probability of success, they're really just referencing which cell of Excel I've put that information in. As opposed to, in this guy right here, oh, why doesn't it tell me? Oh, there we go. This guy right here, I just literally put in the actual numbers themselves. Oh gosh, don't do that to me. There we go. Oh my gosh, stop doing that. I can't click on anything in Excel. I always forget about that. So this is really like the way that I think is better, and let me show you why I think this one is a little bit better right here. The reason this is better is because if you want to screw around with this a little bit, the structure of your computation is already built to be this. So now I can change things, and I can do something like, I'm going to go back and hit enter again here. If I now wanted to say, you know what, I was actually interested in the probability of 3 days of rain out of 5. I can just change this 2 to a 3, and it will auto-update my new probability over here. So I'm going to press 3 and hit enter, and we see it now says, oh, it looks like there's a 30.87% chance that 3 out of 5 days would be rain right there. Right? If I wanted a 4 days out of 5, a 36% chance. 5 days out of 5, about a 16% chance right there. So I think it's more practical for you to write this out with referencing cell numbers where you've typed that in there. So what I typed into this box is literally exactly what you're seeing right there. Equals binom.dist, and then each of these cells that I want to reference. Cell E5 is holding my number of successes, 5. Cell E6 is holding my number of trials, E6. Cell E7 is holding my probability of success, 0.7. And am I looking for a probability that's up to 2 days of rain? No, I'm looking for exactly 2 days of rain. So this is not a cumulative probability. This is a specific one entry probability right here, rather than a probability for an up to amount. Does that make sense there, Jazz? And again, what I am seeing here, and if you're doing this in Excel, it's giving you like little hints as to what to type in. When I just clicked that right there, it just brought up a little thing underneath it that shows me that the 4 comma separated things and the order that they are. So you don't need to like memorize that this goes like successes, trials, probability, cumulative. It will tell you that in Excel every time what you're looking for right there. All right. So and again, I think it's smart for you to like do some setup and then reference cells in here. But again, I can just directly enter in the 257.7 and just get a number out right there also. That's also an acceptable way to go about doing that. Make sense here? So we're going to do a bunch more of these, so you'll still get to see more. And I should change this back to the original one that we had it, since I wanted to reference this as being that 2, the 0.1323, which is exactly what we got a bit ago right there, right? So let me do this. I want to tighten this up so we can see this because I'm about to change the view of my screen right here. And let's go ahead and look at a couple more examples now of doing kind of some similar stuff right here. And in particular, this whole cumulative thing, I'm assuming, is a little bit weirder for us here. So let's go ahead and come back over to Word real quick. But then we're going to do a bunch more of these Excel computations. So I'm going to do more of these, but give me 1 second to get them kind of set up here. So what I'd like to look at for our last things here are the thing to be very careful about is the cumulative thing. So what I'm going to do is state the setups with each of these and then go compute each of them in Excel. So I'm going to write out how I think of the probability statements. Then I'm going to compute those probability statements in Excel. All right. So what I'm seeing here, so we're going to set ourselves up with a new scenario, but it's still a binomial distribution, still has number of trials, number of successes, probability of success, still the same thing. Suppose that 40% of all Eureka residents have earned some college credits in their life, more than 0 college credits on a transcript. What we're going to do is we're going to go out and sample 10 people to find out if they have college credits or not. And so what I'm going to do is I'm going to ask a bunch of questions, and you should see in bold, I'm sort of changing how we ask the question. Exactly 4 people with college credits, at most 4 people, less than 4 people, at least 4 people, between 5 and 7 people. We want to get all the probabilities here that are all associated with this binomial distribution here. So like I said, what I want to do is really just state how do we think about stating this in terms of our probability distribution here. So I am going to, I think I'm on red right now, there we go. What is the probability that exactly 4 people polled have college credits? And let me just say right here real quick, what we have in this case right now is we have that our sample size is 10, our probability of success is 0.4, and in this case we have K, our number of successes is exactly 4 people. So what we're interested in is the probability that we have our variable take on exactly 4. And what I'm going to do to start helping us out right here is I'm going to picture us being on a number line, and all I am interested in is just the probability at 4. This picture is going to make a lot more sense in a second when I draw more comparison pictures right here. Right? So this is where we are not cumulative. So we would put false in the cumulative box there. Now, the difference here in part B, so again, we're going to go into Excel in a minute and compute these, but I want to think about these setups and draw the picture that's associated with thinking about these before. What is the probability that at most 4 people polled have college credits? Well, at most 4 means it could be 0, 1, 2, 3, or 4. So in this case here, I'm thinking that n is 10 still. Our probability of success is still 0.4. But in this case here, k is more like less than or equal to 4. This is at most 4 successes. So in this case, I'm really looking for the probability that our variable takes on a value that is less than or equal to 4. So in this case here, if I picture my number line, this is cumulative. I am really interested in all of the probability, right? And maybe I'll mark my 0 on all these guys, of there being anything between 0 and 4, right? I want to accumulate all of the probability of responses 1, 2, 3, and 4 as well, right? I want all their probabilities, not just one entry's probability. So notice that in this case, then, this is a cumulative probability. We want to accumulate the probability of getting 0, plus the probability of getting 1, plus the probability of getting 2, plus the probability of getting 3, plus the probability of getting 4. Rather than doing an addition of 5 different binomial calculations, we can just tell it, listen, accumulate all of the binomial calculations up until we get the value of 4 here. So this is cumulative. So we'd give true. And notice that this is equal to the probability that x is 0 plus the probability that x is 1 plus the probability x is 2. But this is the more work way, right? Like I don't want to have to write out all these different binomial probabilities in Excel. And so instead of writing out all of them and doing the individuals, we can just put true in the cumulative slot, and it will give us the probability that we see up to and including 4 people with college credits, right? And this picture here is going to be really helpful for us here in 1 second. And what I kind of actually want to indicate right here is I'm going to do this. I'm going to put like an additional like line through this to indicate that we're going up to and including 4. Right? So let's talk through the other ones here, and then we'll go into Excel and see how we get these probabilities out. For part C, we're asking, what is the probability that less than 4 are going to have college credits? So in this case here, we have still n is 10, still p is 0.4, and here we have that k is less than 4. And so here, this is just a kind of a stupid thing with this. Since this is a discrete probability distribution, we know that we can't get like 3.5 people polled having college credits. So what really is the most number of people that we want to consider here? Well, since it has to be less than 4, this is really saying actually like 3 or less. So I'm going to say here the probability that x is less than 4 is the same thing as the probability that x is less than or equal to 3. Because 4 isn't acceptable. I want less than 4. If I got 4 people, that would be sort of like a failure on my part right there. 3 is the largest thing that's a failure. And it is highly desirable for us to state or equal to statements, like that guy, to help us with the computations that we're interested in for this binomial computation here. So in this case, we're going to want to use 3 as our upper bound for k. So when we do this, we'll do our binom dist. Our number of successes will be 3. Our number of trials will be 10. Our probability of success will be 4. And we will say true here for this guy because it is cumulative up through 3. So the reason I'm doing this one is just because less than 4 is an obnoxious way to phrase things when we're in discrete probability distributions, because that means that 4 really isn't the magic number. 3 is the upper bound on the number of acceptable successes for this to be a sort of a true statement here. So we really are looking at 3 being the acceptable number because that's the upper bounds, the highest number of successes we could have, our highest number of yeses we could have to say we did see what we wanted to see, less than 4. So less than or equal to's are better because that way this number will translate to the number of interest to use in our binomial distribution calculator. Now D and E get a little bit weird here. D and E are the reason I've been drawing number line pictures because these are less directly obvious. The thing that we need to see is that when we say that a probability distribution is cumulative, it is always going to accumulate the probability from the left. Always. From the smaller numbers up to what you're working with. Every calculator on Earth always does from the left accumulations up until the boundary, which we saw here of being like 3. This case, we have flipped it. At least 4 means that we want 4, 5, 6, 7, 8, 9, or 10 people to say yes to us. That is sort of like a cumulative probability, but it's an upper cumulative rather than a lower cumulative here, right? So we still have n equals 10. We still have p equals 0.7, but now we have that we want our number of successes to be at least 4, so greater than or equal to 4. So if I'm looking at my probability that x is greater than or equal to 4, we should notice that out of our 0 to 10 right here, we are interested in seeing 4 or more. But what our problem is that that's not the way that this thing works, right? So our probability computation is always going to start at the boundary and go left if we say cumulative. So here's a better way to think about this. This right here represents, this is 1, right? That's 100% of all possibilities is that we're going to get somewhere between 0 and 10 people are going to tell us, yes, I have college credits. What I can do to get at this piece that we actually want is I can subtract off the probability that we get the 0 through 3. This is our 4 through 10, right? So in general, a smart way to do our upper probabilities here, our upper cumulative probabilities, is to think of this as Well, it's all the people that didn't give us those parts right there. This is like saying, well, if you told me, or if I came back with 0, 1, 2, or 3 people having told me that they have college credits, then I would not have satisfied what I'm looking for here to see at least 4 people polled have college credits. So I can sort of do a flip of the scenario that I'm looking for, and always rephrasing things in terms of a less than or equal to is always going to be key for us here, because always, like all semester, every different distribution, all cumulative probabilities we ever compute will always be computing values that are less than the value of interest, never more than the value of interest. So we're always going to need to perform this little flip, the swap out of the 100% total to get the piece of interest. And so here, I want to accumulate this piece. My calculator only gives me areas to the left of a certain value, probability to the left of a certain value. So I'm going to say, start with 100%. Hey, cool infinitesimal prints. I'm just wrapping it up right here, so you're good. I'll see you next week. So we're going to start with 100% and subtract off the parts that we don't want to be left with the parts that we do want, because this we can represent as a lower cumulative percentage. There's no way, calculators just don't do upper cumulative percentages. All calculators do cumulative up to, not cumulative from given a lower bound. It's always the upper bound that we're referencing. So finally, let's look at E and see how we can do E, and then we'll hit Excel and do them and call it a day here. And I'm going to save that last question for later. What is the probability that between 5 and 7 people polled have college credits? Well, I can phrase this one as, what is the probability that our 5 is less than or equal to X is less than or equal to 7? And again, I really want my picture to guide me here. What I'm thinking is that I want between 5 and 7. That's what I want. That's the desired answer right there. But I don't have a way, my calculator doesn't do between 2 values. So what I can do is I can think of, here is my probability that X is less than or equal to 7 amount. Here is my probability that X is less than or equal to 5 amount. And so I can get all of the probability accumulated up to 7. But it turns out I wasn't interested in the stuff up to 5. So I'm actually going to go ahead and ditch that stuff and subtract it off there. So here we can do the probability that we get all of the cumulative stuff up until 7. And we want to chop off all the parts that we don't want. And actually, by the way, I just said another little technicality right here. Notice that I don't want to chop off the probability of getting 5. 5 is acceptable. 5, 6, and 7 are like the responses I want to get. So I'm really looking to remove the responses of 4 or fewer from my probability right there. This will leave me with remaining the probability of getting a 5, a 6, or a 7 right here. So we can do the difference of 2 binomial calculations here to arrive at our result. So let's go pop into Excel and see these computations here, and we will call it a day. And again, just realize that these pictures here are crazy helpful for me for rephrasing these problems into setups that we can actually do in Excel. So I'm going to head over to Excel here, and I'm going to lose my face, but that's okay. I know you guys like looking at me so much, but all right. So let me chop Excel down a little bit right here. All right, cool. So let's go through these kind of one by one here. We've got A, we've got B, we got C, we got D, and we got E. So what I kind of want to do here is use this structure up here that I've set up for myself to help me with each of these here. So what I'm going to do is I'm going to give myself basically like this exact same spread right here, and we'll use this for all of these guys here. So I'm kind of picturing that we're just looking at this right here, and I'm going to use these cells to just change my values. So in A, what we were looking for was, in question A, I was asking for what is the probability that X equals 4? And my successes here, so again, referencing my information over here, I can see that my number of trials in this case is now 10. I'm going to change that. My probability of success for each trial is a 40% chance that each person has earned college credits. And the number of interest, that's exactly the 4 right here. I want to know what the probability that I see 4 successes in my trials here. We've determined that this is not cumulative because I'm looking at exactly that probability of 4. So here's where I'm going to enter in these values to compute this binomial distribution here. So I'm going to now do my equals binom dot to dist. Capitalization does not matter here. When I open a parentheses, Excel is going to continue to remind me of what the structure of each of these guys looks like here. And in fact, let me do this also here. Oh crap, okay, get out of here. Let me throw in one more line to help us with our reminders of what these things look like. So here's how our binomial statement always is going to work right here. Why did it pump me over? Seriously? I can't move it? What? Is it really in this one? Why did that get moved like that? Okay, there we go. So this is how we use the binomial distribution calculation. I just didn't stick the equal sign in front of it because I'm not doing a calculation right here, but I do want to do a calculation here. So equals binom.dist. The successes here is D9. The trials here we have in D10. The probability of success here we have as, oh gosh, I don't really want to do this way, I guess, do I? Because I don't want to change the numbers and change my old responses. Okay, I'm not going to do the table thing right here. Our successes of interest here is 4. Our number of trials in this case is 10. Our probability of success is 0.4. And we are going to go false for cumulative because we just want to know exactly the 0.4. And that's going to tell us about a 25% chance right there. In B, we are looking at the probability that X is less than, and I'll denote this as less than or equal to 4. It's a less than symbol with an equal to symbol next to it. Probability that we see less than or equal to 4. So we're going to get almost the exact same computation right here. The only difference, and honestly, that's what I should just do, is I'm going to copy exactly what I have here into, oh gosh, what are you doing to me? Oh gosh, get out every time. I just want to keep going with what I've got here. It's not allowed. Copy. Okay, we're back to you being happy. Now I'm going to come down here and paste it in. But down here, notice that I want to change one part of this, right? Still 4 is my number of successes as my boundary. Still doing 10 trials. Still a 40% chance per trial. But in this case now, I want to know up to and including 4. So I'm just going to change this to true. And we should be certainly getting a larger probability since it's talking about all of the probabilities of 0 plus 1 plus 2 plus 3 plus 4. And so now we're seeing that there's a 63% chance that I will come back with between 0 and 4 people having reported to me that they have some college credits. If we look at C here, what is the probability that we're going to get less than 4? And so here I think it's worth just noting this. Probability that X is less than 4 is equal to the probability that X is less than or equal to 3 because we are in a discrete probability distribution. We sort of jump directly from 3 to 4 because we can't have anything in between. Again, I'm just going to copy this guy right here. This guy. Oh, really? And again, in this case now, the only difference is our upper bound number of successes is just 3. We still have 10 trials. We still have a 40% chance of probability of a success. In this case, since we're looking for, oh no, this was cumulative. I was just backspacing through that, but it still is cumulative because we want to know up until 3. 0, 1, 2, and 3 are all our possible acceptable responses here. So this is a cumulative up through 3. And so it is true for cumulative, and we'll end up seeing that Excel is going to give us this about a 38% chance that we see up to 3 as our up through 3 as our number of people with college credits. Finally, number 4 is, or D and E are the ones that are a little bit hairier here, but I really want to encourage you to think about these pictures that I'm drawing right here, to think about where your probability lives. If I want the probability that x is going to be greater than or equal to 4, that's really the same thing as chopping off the probability from 1, from 100%, that x is less than or equal to 3, right? It's saying 4 and above, all the other parts are 3 and below. So we can do this as a below computation. We always have to have the less than or equal to whenever we're thinking about these. It's always left cumulative parts here. So the way that I'm going to compute this answer is equals 1 minus our binomial distribution. Our number of successes of interest here is 3, right? Because that's what we're trying to chop off. Number of trials is 10. Probability of success is 0.4. Is it cumulative up until 3? Yes. So we're going to get a true in here. So we're saying to get the parts from 4 and above, chop off the parts from 3 and below from 100%. And this is going to tell us we're going to see about a 62% response right here. 0.618 right here is what I'm looking at for that answer right there. Finally, for E, we can do a pretty similar thing here. If I want to know what is the probability that we see a 5, a 6, or a 7, and in fact, I'm going to do this one 2 different ways just to emphasize to you how we're thinking about this. 5 is less than or equal to x is less than or equal to 7. There's 2 ways I can think about this. I'm going to just go ahead and hit enter here. I can either think about this as being equal to the probability that x is less than or equal to 7 minus the probability that x is less than or equal to 4. This will leave us remaining with 5, 6, and 7 survive. That's what we want. We'll do that one in 1 second. Wait, really? Oh, I stuck the equals in front. Equals means do a computation, and that's not what I wanted Excel to do. Stop putting an equals in front of that. What's... No equals, just text. Okay. Alternatively, a different way that I could think about this guy. Here's what I really... I'm not going to do that. That's what I should do. I'm going to put this right here. Another way that we could phrase this is that this should be equal to the probability that x is equal to 5, tighten that up a little bit, plus the probability that x is equal to 6, plus the probability that x is equal to 7, right? It's just typically a pain to add up all the individuals right there, so nobody ever really does that. So let's do this computation both ways in Excel here and see that both of them are going to give us this exact same answer right here. So here I want to do equals binom.dist. Our number of successes is 7. Trials is 10. Probability of success is 0.4. Is it cumulative up to 7? Yes. We want to subtract from this a binom.dist of up through 4 successes out of 10 trials with a probability of 40%, and cumulative because it's up through that 4 as the number of trials. So this is saying accumulate all the probability up through 7, but then chop off the probability that you accumulated up through 4 so that we only have remaining the probability of 5 through 7. That's going to give me a 0.3546, 35.46% chance of getting getting 5, 6, or 7 people that tell us they have college credits. I do want to show you that we can do this another way, binom.dist. This would be the number of successes is exactly 5 out of 10 trials with a 0.4 probability of success. Cumulative, false, because in this setting, I just want to get exactly the probability of 5 plus the binomial. I'm going to do this here so it'll give me the next line. Binom.dist of 6, 10.4, false, plus binom.dist 7, 10.4, false. Now what I am expecting is this certainly should give me the 0.3546 that we just saw above, and it certainly does right there. So what you guys need to know, if you are looking for more help with this, if you don't like what just happened right here, I am going to post this Excel document and this Word document in the video stuff in Canvas. And what you need to know is that you can double click on any one of these numbers and it will show you exactly what I typed in here, and you can modify what I typed in up there, right? So you can kind of pick these back apart to see what I did and figure out for yourself why I did what I did. And let me just delete that because we didn't actually end up doing that right there. Notice that, remember in our early one, I directly referenced cells, which might be easy if you're working with the same scenario all the time. Down here, we kept on changing the scenario, so it wasn't as useful for me to do this in cell format right there, meaning referencing the cells. So here, we just directly typed in the numbers. Here we referenced cells in Excel. Either way is acceptable because Excel is down with both. So again, if you're a little lost, I'm going to post this right here so you can double click on any one of these computed numbers and see exactly what I typed in to get it, and ask yourself, why did he type in exactly that to get that guy right there? So I'm going to wrap it up because I know this one's been a little bit long here today. And I will see you guys if you have questions. Obviously, we got a little bit more exciting things happening this week, so I expect I might actually get some more good questions here in our Zoom office hours. Just coming back to my face here to close this off right here again, I will post both these documents so that you can take a look at these guys here, because I know it'll be helpful for you to see what did I do in Excel. So take a look at those guys, and I will see you guys in email, in My Open Math, in office hours, or